In this video, we're given a curve e to the negative x squared, so it's this simple Gaussian thing. And then we're told that this region is defined by this Gaussian curve, the x-axis, the y-axis, and this little line segment x equals 1. We're then told that this region is revolved around the y-axis to define a solid of revolution, and we want to use cylindrical shells to get the volume of this solid. So the problem asks you to sketch this resulting solid. And my hand drawings are subpar, so I just did it in advance. So we just had this region over here. We spun it around the y-axis and it swept out this three-dimensional space, and I've already put a shell in there as well. So note that the shell shares the same symmetry axis as the solid itself. Now the idea is the solid could be broken into infinitely many nested shells to exactly recreate this shape. And we're going to use an integral to just add up the volume of all of those shells and find the volume of the entire shape. So to start things out, this particular shell we're looking at has its radius defined by the location of the right-hand side of it, and that's x. Next, the height of that shell is given by the y value corresponding to that x. Well, what determines the y value? It's this curve e to the negative x squared. Finally, the thickness of the wall of our shell is given by dx. So to write down the volume contribution given by this particular shell, we're going to cut it and unroll it. And when we do that, we get a slab, and it looks like this. And we call the volume of this slab dV. It's an infinitesimal volume contribution to the total volume of the solid. The height of this slab is given by e to the negative x squared. Again, that's the y value corresponding to x. And the length of this slab corresponds to the circumference of the original rolled up shell. Well, with a radius of x, that circumference must be 2 pi x. And then finally, I have my thickness dimension, and that's just a little dx. Now it's very simple to find the volume of a rectangular solid. You just multiply the three dimensions. So I have 2 pi x e to the negative x squared dx. Now one of the really important points with physical integration is that integrals are really just a summation device. So the total volume is just going to be the sum of all of the volume contributions, those dv's. But I have an expression for those now entirely in terms of x. Since my dv has been expressed entirely in terms of one variable, I can now put the limits of integration on this in terms of x. And in this case, our x's start out all the way at the center here at x equals 0, and then they finish all the way over here at x equals 1. Now it's time to actually grind through the integral, and I noticed something in here that makes me really happy. I have a function of a function, e to the negative x squared, and the derivative of the inner function there is negative 2x. That's the derivative of the exponent. And I see a way that I can build negative 2x right in front of it. So I'm going to be able to recognize the chain rule backwards and avoid doing any explicit substitutions here. Again, I want a negative 2x in front of this exponential term. And so I'm going to move the pi out. And I need that to be a negative 2x. So I'm going to multiply the interior by negative 1 and the exterior by negative 1. And so there's no need for an explicit substitution here. The antiderivative of that integrand is e to the negative x squared. Try it for yourself real quick. If I differentiate e to the negative x squared, I get e to the negative x squared multiplied by the derivative of negative x squared, which is exactly what I started with back here. We're going to evaluate the antiderivative across the endpoints. And when I plug in the upper limit, I get e to the negative 1. And when I plug in the lower limit, I get e to the 0, which is 1. It's a little bit nicer if we distribute a negative 1 through that difference, and I can write it as pi times 1 minus e to the negative 1, which is 1 over e. And I think that's a fine place to leave the answer. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.